Okay, so welcome back, and thank you for, I'm happy to see so many people that stayed for the whole week, so thanks a lot for your presence. And it's my great pleasure to announce the closing lecture of this ALGA. Jorge Vitório Pereira, here from IMPA, who will speak on closed meromorphic one-forms. Please, Jorge.
Thank you very much for the opportunity to share some math with you. And I think we could start by thanking the organizers for the wonderful conference and for the very great, nice week, right? So I will apologize because my slides are not as great as Marau's, but come on, we do what we can. So next conference, I want to speak before Marau, please. And so I'm going to talk about closed meromorphic one-forms. I will try to be not very informal. Will be informal discussion about these objects. And I will try to use them to give some intuition for you of what a foliation, or at least a codimensional one foliation, look like. So what's the motivation? So we already saw the definition of foliations in several talks. So we are going to consider a subsheaf. We consider a subsheaf of the tangent sheaf, a coherent subsheaf, which is closed under Lie bracket, and whose cokernel is locally free. I don't like to call the cokernel of this inclusion the normal. I prefer to call the double dual the normal, but it doesn't make a big difference. It's not very relevant in this talk. And as already mentioned by several speakers, Frobenius' theorem says that away from the singularities of Tx over Tf, the singularities of the foliation, we can see locally in the analytic topology Tf as the relative tangent sheaf of fibration, of a germ of a fibration, defined in the analytic category. So this gives a very good picture, a very good description of the foliation in an analytic neighborhood of a smooth point. And nobody seems to really know what happens at Sim F. And probably when we are first seeing these objects, this seems to be quite a mysterious question. But I will try to explain how we can get some intuition on what is happening there, at least for the case where Tx over Tf has rank 1, the case of codimensional one foliation. And for that, I will ask you to have a bit of patience, and let's talk about something very classical, very well known for everybody, differential forms, closed differential forms. And I want to start discussing their residues. So I will be considering a smooth complex variety. If you don't like complex variety, you can think that you're in the algebraic category, but it's really not important. And I will just take a meromorphic one form on X. So it's some object that has a divisor of poles, a locally finite sum of reducible divisors with positive coefficients. And if we have one of these divisors, we can just take a small transverse, a small disk transverse to X. So you see here, I is the new tau, right? So this I is equal to tau. And I'm trying to draw H here is 1 is a reducible hyper surface, and I'm just taking an holomorphic disk transverse to Y. And we define the closeness of omega. We are assuming that omega is closed. Allow us to define this integral, which we call the residue of omega along Hi. And it does not depend on the choices of the point, of the disk. I'm sorry, this is not easy to read, but I will not use this again. And anyway, so remembering what is the definition, and we will denote this whole thing, the sum of HI with the coefficients, the residue divisor of omega. Okay, so this is a divisor with complex coefficients, an element in DVX tensor C, which most of you probably already saw when studying Riemanns surface, the simplest case, the case of dimension 1. And we know that if X is a compact Riemanns surface, then the degree of this divisor, just the sum of residue of omega over its poles, is equal to 0. So I want to start my discussions thinking on a higher dimensional version of it. And for that, it's important to reinterpret this formula. There are several ways to do, and perhaps the most natural one is this. So we can think the divisor as determining an element in the cohomology of X with coefficients in C, here denote H2C, by essentially integration, right? So we can, given any two cycle, we can just intersect these two cycles with the irreducible components of D, of the support of D, the HIs, and add up the result with the coefficients of D. So the divisor determine a class in this cohomology group that we are going to call the Chern class of D, for other reasons, just a name. And there is this very, very nice result, which generalizes the previous result. It's a result by Andrea Vale, who says that if I have a closed meromorphic one-form or a smooth complex variety, then the Chern class is equal to 0. Note that there are no assumptions of compactness. I'm just looking at X, a complex variety, a complex manifold. I will explain the proof of this theorem. It's very nice and very, very, let's say, simple. But before that, I would like just to make a small comment. You see, this is a reproduction. The title there I took from the original paper, and you can see the address of Andrea Vale. He was at USP when he proved this result. So he spent the year of, he was at USP from 45 to 47. He came here before the war ended. There is even in his book, he tells a passage where he moved from São Paulo to France to go to Paris to attend to some seminars before the end of the war, and when he came back, he got the news of the bombing in Hiroshima and so on. But anyway, I really recommend this.
The first edition of Foundations was São Paulo, but then they annihilated this forever in the US.
Oh.
Never appeared again in São Paulo.
I didn't know that.
It's terrible.
Yeah, he met Zariski here in São Paulo, and it's a very nice history, and I really recommend this book. It's very interesting. And the funny thing is that it ends, the last page is he leaving São Paulo. So the end of his apprenticeship was here in Brazil. So, and also for those that are looking for jobs, it's quite, I would say, heartwarming to read this, because he came to São Paulo because he had a really awful job in the US, was having a hard time to have a position, and he came here, and he went back to Chicago. But anyway, how the proof goes. So the proof is very simple. So let's start with just any class in H2, and we can represent this by a sum of simplex, right? So the simplex are just the maps from the two-dimensional simplex. We can think as a triangle in R2, 2x, and just doing the usual perturbation that we do in differential topology or in topology, we can assume that each of these guys will intersect the support of the residue either nowhere or either in an interior point. So we can represent the boundary of sigma j as a sum of gamma i's, which are these paths around the HIs, with some coefficients determined by the intersection number of HI and sigma j. This will be just plus or minus 1 if the intersection here is transverse. And so we can represent the residue as this sum. But since we are taking an element in H2xz as a representant, right? So the boundary is 0. And so I can write the sum of residues of this residue as minus the points where sigma j and residue of omega is equal to empty set. And so this is 0 by Stokes' theorem. The boundary here becomes d omega, but d omega is 0 by assumption, and that's it. That's his proof. Completely elementary, and with lots of implications as things usually happen in mathematics. Okay, so it's also important to have a twisted version of these objects in order to give this intuition about foliation. So the twisted version I want to talk about are the meromorphic flat connections. So these are things that, ways to differentiate sections of line bundles, or for what matter, could be any sheaf, any coherent sheaf, but here I want to focus on rank 1 connections. So I'll take L to be a line bundle, and a meromorphic flat connection is just an object that takes a section of L and produces one form with coefficients in L. So it's an object that's not O-linear, it's a differentiation. So it's only C-linear, and satisfies the Leibniz rule. What's the relation with the holomorphic forms? Well, locally these things can be written. If I just take a local generator of L, then I write down what nabla should be. You see that it's completely, the Leibniz rule implies that it's completely determined by the value on S, and the ambiguity is this one. And so you have the usual differentiation on F, and also the result of applying nabla to S, which is a one form that I'm denoting here to eta u. And this is the connection. It's one form that depends on the trivialization that we chose, but then you can differentiate this eta, take the exterior derivative. It's intrinsic, does not depend on the choices, and it's called the curvature of connection. And we say that the connection is flat if and only if this curvature is 0. So flat connections are the twisted version of closed meromorphic one forms. And a corollary of Weil's theorem is this residue theorem for connections that says that the Chern class of a line bundle endowed with a connection is minus the Chern class of the residue of nabla. If L nabla is flat, it's locally defined by closed meromorphic one forms, and they are not intrinsically attached to nabla, but the residues are. So this right-hand side makes sense. It's intrinsically attached to nabla, and you recover the residue theorem. So the proof is essentially to realize that to give nabla is the same thing as giving a certain closed meromorphic one form on the total space of L. I will not do the details, but that's how it goes, and it's really, you write things down and you realize that. And you see, even if we are interested on compact complex manifold, it's important to have Weil's result, which has no compactness assumption, because here we had to apply it on the total space of a line bundle. It will never be compact. But anyway. And so, as I said, why this will help you understand foliation theory? Well, first of all, I think this is one of the most natural, the most natural example of foliation is, of course, the foliation by points, right? A connection of points, the TF equals 0, it's very easy to understand. If you go one step beyond, you can also think of the foliation with just one leaf. You take TF equal to TX, it's also foliation. So this we think we are used to, and we understand it as much as we understand varieties. But then if you go to codimension 1 or dimension 1, we already saw this very simple class of foliations, which are the algebraically integrable foliations, which are essentially the ones defined by global morphisms. So these are arguably perhaps the simplest class of foliations besides the dimension and codimension 0. And what come next? I would say that this is the class of foliation that comes more natural. The foliations defined by closed meromorphic one-forms. They are not trivial. They can even have dynamics. They are not necessarily, the leaves are not necessarily algebraic, but they are still, we can still have a quite good grasp of what they are. And so if you want just to relate with the previous definition, we start with a closed meromorphic one-form omega. We can contract vector fields on X to obtain a section of this line bundle, which will be surjective in codimension 1, not surjective, because you have to tensor by the ideal of the singular set of F to have a surjectivity. But anyway, that's an example. And that's the example that I want to focus to say things and use it as a good toy model of what a foliation should look like. And one other thing, another example that also is very relevant is that when I have age and invariant hypersurface, we are always here in codimension 1. I'm not saying that age is a leaf because I will allow it to contain part of the singular set of F. But if age is an invariant hypersurface, then we can prove rather easily, Bott did for us, that age carries a flat meromorphic connection. Not age here, sorry. It's the normal bundle of age, or the normal bundle of F restricted to age carries a flat meromorphic section. Oh, here. And this is called Bott's connection. And it will play it plays a huge role in the theory of foliations, and will play a role also in the discussion that I'm planning to carry out here today. So just to give an example, I will start with some kind of silly example, but please allow me to, in order to be very simple. So I will start with this foliation, the foliation defined by this closed one form, alpha dx over x plus beta dy over y plus gamma dz over z. Alpha, beta, and gamma, non-zero complex numbers. So this is a closed one form. I'm multiplying by x, y, z just to have a holomorphic one form, but I could just consider this case. And then I can look at, let's say, x equals 0. X equals 0 is an invariant hypersurface for this foliation. And essentially, by trying to erase this dx over x to be able to talk about the restriction of these things here, you can do some manipulation to see that this Bott's connection is the one that has this logarithm defined by the logarithmic form like that. But this is, Bott's connection is defined, is a closed meromorphic, it's a flat meromorphic connection on the normal bundle of the foliation restricted to age. We don't, even in the case that F itself is not defined by closed meromorphic one form. It's a kind of linearization of F along an invariant hypersurface. And the nice thing is that we have, for instance, residue theorem, which are just reinterpretation of Weyl's residue formula. So we saw that Weyl's residue formula gives a way to write the Chern class of a line bundle in terms of the residue of a connection. In the case of foliation, we have a natural connection defined by Bott. And then if you just combine these two things, the connection defined by Bott with Weyl's residue theorem, we obtain a residue theorem for the normal bundle of F in an invariant hypersurface. Okay? No, this is an immediate application of Weyl's theorem. All these things appeared in foliation theory, regardless of Weyl's theorem. So what I'm doing here is just trying to connecting the dots and giving very simple proofs of these results, which are not that hard, but now at least we know where they are coming from. And so this result also, with some extra work, becomes Camacho-Sard residue formula, but in greater generality. But anyway, the point here is that I can write down the residues, or I can write down the Chern class of the normal bundle along Y, which is some element of cohomology H2 with rational coefficients, in terms of a combination of Chern class of components of the singular set with coefficients that come from the, can be expressed in terms of the quotient of eigenvalues of the singularity, or something like that. Okay? Okay. Very good. So now we can try to look a little bit closer to this closed meromorphic one forms and try to simplify them by applying birational transformations. And what we have already from the definition of residues, we can always take a one form locally, right? I'm working in a neighborhood of a point, analytic neighborhood. We can take the hypersurface passing through that point, look at their residues, consider this natural logarithmic differential, subtract from omega, and we obtain a meromorphic one form without residues. We see that being without residues is equivalent to being exact, so we can write this, we have this expression for FG local holomorphic functions, HI also, something like that. And we can attach to omega an ideal. Right? This F and G are not intrinsically defined. There's some choice involved. But the ideal generated by them is intrinsically attached to omega. Right? That's what we call the base ideal. We also have the residue divisor that we already talked about. And we can make a technical definition of what is resonant or not. I don't want to get into this. I will just skip it. Okay? But from this expression, we can simplify and have base ideal and residue. And we can propose a definition. Definition is that what would be simple. So a simple singularity would be some singularity where the base ideal is trivial, meaning F and G has no common zeros. This F over G will have no indeterminacy points. And also we can also assume that the support of the polar divisor is simple normal crossing, and we also impose a condition of non-resonance. And we have this proposition theorem. Proposition because the proof is easy, and we put together a lot of very hard theorems. And you have that after a locally finite composition of blow-ups along smooth centers, we can start with any closed meromorphic one form, end up with a closed meromorphic one form with simple singularities. So this simplifies a lot the situation. It's fair to say that I'm not clarifying the singularities of an arbitrary one form, but at least I'm really explaining what they are up to birational transformations, up to blow-ups. And we can even transform the definition something very concrete. So locally, we can always write like that. We can always find singularity, local system coordinates, x1 in the analytic topology, x1 to xn, and write omega as something like that, plus some condition of non-resonance on the lambda that I don't want to get into. Okay? So in particular, this is saying that near the polar set, the singularities are very, very simple, because they will appear only in the crossing of these invariant hyperplanes, and outside of it, even if it might be quite complicated, the singular set, the form will be exact near it. Okay? So this somehow says that, well, at least if I'm interested in these foliations of codimension 1 defined by closed meromorphic one forms, if I want to understand them, if the problem that I'm looking at allow me to compose with composition of blow-ups along smooth centers, I can assume that they are locally like that. And I think this helps a lot. So if you see a singularity of codimension 1 foliation, I will say, well, perhaps they are similar to this, even if this is the model that appears for closed meromorphic one forms. And what is surprising is that exactly the case, at least in dimension 3, codimension 1 foliations in dimension 3, they have local models which are formally equivalent to what we just saw. In the original paper, this is an extract for the original paper of Felipe Cano in Annals of Mathematics about the resolution of singularities, where he gives a definition what is the simple singularities for arbitrary foliation. But as I learned from his works and works of Dominique Servoz, this complicated definition can be simplified to just something like that. So a simple singularity for any foliation is, by definition, something which is in the formal completion of a point conjugated to that. So there exists a system of formal coordinates that the foliation will be defined by a form like that. So even if this is a very restricted class of foliation, this is a very general at the same time, because these are the local formal models of a singularity of foliation. There is nothing much more complicated than that. Of course, there is the discrepancy between the formal classification and the analytic classification is huge. That's, some Fields medal were given because of that, but the formal classification is that. Okay. That's one of the great reasons I think that we should think about foliations defined by closed meromorphic form, because they are actually.
So this is in the completion.
In the completion. But anyway, that's what I'm saying. Formally equivalent to closed meromorphic one form with simple singularities. And then there is this very useful, a very nice result by Felipe Cano, which in dimension 2 was done due to Seidenberg, which is not that hard, but dimension 3, there is a first version by Dominique Servoz and Felipe Cano for what they call non-dicritical foliations, which is already hard, and there is a very hard case, which is the general case by Felipe Cano, which says that after blowing up, every singularity becomes simple.
What was the language of Seidenberg?
It was very close to, it's really vector fields. Yeah. Because he's in dimension 2, right? So every foliation, the ambient space here is always smooth. So rank 1, we are talking about objects defined by TF is locally free, generated by one element. So it's a vector field. Very good. So why they did that? So at the beginning, right, there is this Cano-Servoz result that was for foliations that I said that was non-dicritical. They did that because they were interested in that, and the existence of separatrixes, which was a conjecture by Renato, a series of problems on foliation theory raised by Renato. And one of them was that the existence of separatrix, germ of hypersurface passing through singular points, invariant by the foliation. And this was proved by Camacho-Sad in dimension 2 using the index theorem, which is a version of that Sua's result, and that they proved before. And then there is this result by Cano-Servoz in dimension 3 and Cano-Matte in dimension 4, that when we have non-dicritical foliations, we always have this existence of separatrices. Okay? And the funny thing is that if you drop this non-dicritical, there are examples by Joannoulou of dicritical foliations which have no separatrix. And curiously, this existence of dicritical foliation without separatrix is related to the algebraicity or non-algebraicity of leaves of foliations in lower dimensional varieties. But anyway, so this was a huge result. Both were huge results on the subject and are extremely useful to carry out the MMP and a lot of things. And what I want to discuss is just to mix all these ideas that we are discussing to give an example, a simple criterion for the algebraicity of the separatrix. So far, we are discussing everything locally analytic. So now I want to look at a foliation defined on a projective manifold. And I will take a foliation f defined on it. And what I want is to consider foliation that I will do only one assumption. I will assume that there is one point on x, P, where my foliation is defined by something that starts like a generic closed meromorphic one form with poles on x, y, z. Simple poles and that. So I will assume that my omega is this, alpha, x, y, no, yz, dx plus beta, xy, dz, or xz, dy, plus gamma, y, xy, dz. Okay? And now we can put anything after that. Of course, I'm assuming that my foliation is integrable, something, but I'm just prescribing the first non-zero jet of my omega at a singularity. And then what I'm claiming, right, this is assumption on this, there's no assumption here. What I claim is that if this alpha, beta, gamma are Z linearly independent, I mean that the Z model generated by alpha, beta, and gamma has rank 3, I claim that through P, I have 3 invariant hypersurfaces, algebraic hypersurface. Just like that. And I will explain the proof. The proof is a funny thing. How does this thing goes? So the first thing is that I can apply Kano result and reduce to the case where my foliation has simple singularity. And moreover, I can do that without changing the behavior of f in a neighborhood of P, because P is already a simple singularity. I have just to blow up away from P. Then there is this result by Kano-Servo about the existence of a separatrix that allows me to do something very nice. So I will just choose one of these planes. I chose there z equals 0. I will choose one of these planes. So I will have here the singular set will look something like this at the neighborhood of this point. So I'm choosing z equals 0. And this Kano-Servo theorem of existence of separatrix tells me that here the z equals 0 plane, so my picture is not very good, the drawing is not very good, so this z equals 0 is a germ of surface. And moreover, I can just extend this to a germ of surface S, that's what I'm worried. Yes, there's a germ of surface S, which contains which intersects the singular set in a compact curve inside of it. So I have this S with some compact part of the singular set contained in it, and that's it. So we have S and a compact divisor on S. S a priori is only analytic. Okay? So I'm saying that I can construct this germ of surface which intersects the singular set of F in a compact divisor, in a compact set, and contains this thing. And then my assumption, what we have now. So I have this surface S, and on this surface S, what I have Bot's connection. And what I know that from the residue formula that I explained, that the residue of the normal bundle of F restricted to S will be a sum of some residues where C are the connected components irreducible components of the singular set of F restricted to S. The Chern class of C. Okay. So you look at this formula. So this guy belongs to H2 S tensor Q. And these are elements in H2 S tensor Q. And these are complex numbers. And so what you see is that you have the assumptions on the rank of the Z module generated by alpha, beta, gamma is saying something about the solutions. It's saying that I have a solution. These guys will be written in function of alpha, beta, and gamma. There will be one of these guys, the guy corresponding to the residue along this guy and this guy. That was the example that I wrote. Will be something like 1 minus alpha over beta and 1 minus gamma over beta, or something like that. And so I know that I have a solution to a linear equation defined over Q with guys which are not on Q. So this already says that the solution set has large dimension. And from that, I can produce more than one solution and end up producing, with some simple linear algebra, producing a divisor supported on this curve which has positive self-intersection. I'm saying that my assumptions allows me to produce a germ of surface containing a divisor with positive self-intersection. And then classical work by Hartshorne and Andreotti is sufficient to imply the algebraicity of a surface like that. And this gives the algebraicity of this leaf, of this subvariety, and the same argument will apply to the other three, and you get three algebraicity criterions. So this is part of a kind of a mixture of survey and research work that I did recently, and if you want, you can look for these details of this argument and also several other results in archive. I think since this is the last talk, it's not bad just to end 2 minutes before the finish. So thank you.